Welcome. Let's learn about sensitivity report in a linear optimization problem. So imagine you are the owner of this hot tub manufacturing company called Blue Ridge, and you manufacture different types of hot tubs. Yeah, you have a type of hot tub that's called Aqua Spa. You have a type of hot tub called Hydrolux, which is a deluxe version. And then you have this third one, which is a Typhoon Lagoons, which is even more fancy version of this hot tub. I use a lot of these examples from the textbook Ragsdale, so a lot of credit to this book and this author, Cliff Ragsdale. And this comes from that textbook that I use as one of the textbooks for my class. So imagine now that you are this manufacturing company and you're trying to decide what quantities of each of these products you should build so that you maximize your profits. Yeah, and you have these decisions to make as to X1 being how much to build of Aqua Spa, X2 being how much to build for Hydrolux, X3 being how much to build for Typhoon Lagoons. Well, you have constraints which says, hey, for you to build 1 unit of Aqua Spa, you need 1 pump, 9 hours of labor, 12 feet of tubing, and each of these Aqua Spa hot tubs will make you $350. Likewise, you have unit economics for how much the profit contribution is for Hydrolux and for Typhoon Lagoons. And each of them require different amount of tubing and labor. So this is just a simple example that gets you start to think about decisions that you need to make, which is these decision variables, constraints that you have, real life constraints. Typically, any constraint there'll be not just few of these constraints. There could be 50, hundreds of constraints that you might have on building something. You might not even have the right amount of electricity, let's say, to do your manufacturing. So that could be all of those constraints, yeah? And you would have ultimately something that you care about, the objective, which is profit maximization in this case, or it could be cost reduction, could be another objective. So this is the situation, and we want to find out, not only do we want to know like what quantities of these to produce, but we also want to know how sensitive is this decision if I say I model this linear programming problem with this mathematical model, and we've seen this in the past video, a version of this. So take a look at that as to how we solve a linear programming problem. But let's say we can write this mathematical model that says, hey, we will choose X1, X2, X3, that the output will be from a linear optimization problem. And we know what we need to optimize for this decision, which is I want the maximization of profits. Each unit of X1 is 350 units, X2 is $300, and then X3 is $320. So we have some sort of an objective that we've translated from the profit maximization. We have decision variables, and we have certain constraints that we have expressed. Once we translate this real life situation into a mathematical model like this, which is we might have constraints around how many pumps, right? We might be given that you only have 200 pumps, and that if you want to produce X1 of Aqua Spa, X2 of Hydrolux, X3 of Typhoon Lagoons, each would use 1 unit. So you might be given more constraints here, which is how many pumps do I have, how many labor hours do I have, and how much tubing feet do I have, yeah? So given this business situation with this constraint, you would first want to do what I just did. You'd want to have the mathematical model that says, hey, how do I translate this business situation into a mathematical linear optimization problem? And I'll feed this into Analytic Solver. Once I have this, I can easily go to Excel and actually write that down. Say, hey, these are my constraints. These are for each of these Aqua Spas, which is this column here, I would need 1 pump, 9 laborers, and 12 feet of tubing, and it'll give me $350. And likewise, I have for Hydrolux and Typhoon Lagoons. I can actually solve this, and Excel with using linear optimization with the simplex method will tell us that, hey, you should be producing 122 units of EquaSpa, which is 122 units of X1. So it will solve for this and it will give us this variable that we're looking for as to what unknown variable these are. How much should you produce of each of these so that you maximize your profits? So it already solves this for you, and that's the video that I also have created, how to go about formulating a linear optimization problem. So that's a separate video that actually goes about the entire setup. So take a look at that. But assuming you know how to do this, Excel Analytic Solver will already tell you that, hey, you should be producing 0 of Typhoon Lagoons, 122 units of EquaSpa, and 78 of Hydrolux. And we can also tell it like, hey, use the linear programming standard LP quadratic engine to do this calculation, and we'll also tell it to use non-negativity constraint. So when we run this report, yeah, it will, when we run this optimization, if you go to Analytics Solver and then you say optimize, solve complete problem, it will run this problem and it'll give us this answer. But at the same time, you can also generate a sensitivity report. So you go to reports, optimization, sensitivity report. If I click that, I will get a sensitivity report that looks like this, a new tab that gets created, and it'll tell us a lot more information. So why do we need a sensitivity report? Well, this is one decision. Yeah, it tells you make 122 units of EquaSpa, 78 units of Hydrolux, and it assumes some of these constraints are fixed. Yeah. But in real life, a lot of times, profit contributions can change. The constraints around laborers could change. What you assumed right now may not be true in a week. So we want to know answers to how will my optimal solution change if some of my constraints are changing. So that's what sensitivity report will tell us. It'll tell us what is the impact of this optimum solution changing if some of these constraints change. Yeah. So let's look at how we can go about this. It will generate this report for you. And so I've taken a screenshot of this report, and I've also taken this linear optimization problem into a slide deck. So let's go to the slide deck, and I'll show you and walk you through each of these parts of the report. So assuming you understand the business situation and you understand how to write the mathematical model that translates the business situation, and now you've solved a linear optimization problem and gotten a solution, an ideal optimal solution. Now you're trying to ask questions, what if questions, like what if this happens, what if that happens, what if my, the number of pumps reduce or increase, how can I change my profits, what if my contribution of each of these profit for each of these products change, how will that increase or decrease my decision variables that I have already chosen. So let's look at and answer some of those questions. So I told you how to generate the sensitivity report. You go to, first you optimize and solve the complete problem using the linear optimization LP engine. Once you do this optimization, you will be able to click the report, which is this part, and it will create a new sheet, Excel sheet, which will have the sensitivity report. By clicking optimization, once you click report, you click optimization and go to sensitivity report, and that will insert a new sheet, which is the sensitivity report sheet. Yeah. Once you do that, you might have this error sometimes, which is the report is not available. So if you ran the optimization and didn't click the report soon after, you'd have to run the optimization again, and then it will actually be able to see it. But assuming now that you have this sheet, you will see this type of a report. So now let's understand every part of this report. Yeah. So the goal of this is to generate the sensitivity report. I showed you how to do it. And second, understand all aspects of the sensitivity report so that we can answer questions. What happens to my optimum solution if some of these constraints, some of these coefficients change? Coefficients around these known variables, the coefficients around what is the profit margin. Let's say some of these change. How will it change my optimum solution? So let's take a look and understand the sensitivity report in detail. The first step to know is that the sensitivity report has three parts. It has information about the objective cell, or whatever your objective function is, which is this part. We want to maximize profits. So it tells you clearly that you will have $66,100, and that matches to what was outputted here. So the maximum profit is 66,100. Yeah. So the second part of this is the decision variable cells, and then the third part is constraint. So it matches one to one. Yeah. We have the objective, which goes here. Decision variables in green, it talks about those variables here, and constraints all in yellow goes here. So there's a one-to-one mapping for each of these areas. And if you remember, we also have the same one-to-one mapping in the optimization model, where we have the decision, constraints, objective. Yeah, same thing. Decision, constraints, objective. So you see those three parts consistently show up. So those are the three parts to any sensitivity report. Yeah. So now let's look at each of these parts in one by one detail. Let's go to the first one. As I said earlier, objective cell. This is the objective cell. Final value stands for what is the total maximum profit you can make in this situation. I have a maximization problem, it gives us the maximum value. If you had a minimization problem, it gives you the minimum value that you're hoping to get. Let's say you were reducing costs. So it gives you the final value and matches out to your Excel sheet as well. Yeah. The second part, so the objective final value is the final result. Yeah. In case we want to maximize, as I said, maximize the profit, minimize costs. The second part is the final value within the decision variable cells. Yeah, there's a final value for each of these. It tells you all of the decisions that you've taken. Yeah, decision variable cells final value stands for the final value, the results of your decision. So if you see 122, it's telling you make 122 aquaspas, 78 hydrolux. That's what this is. It's telling you make these products. This is the final value of the decisions. So for the decision variable cells, tells you aquaspas make 122, hydrolux make 78, typhoon lagoons make 0. So that's how you interpret this first column of decision variable cells. Yeah? These are the variables, and let's look at how to interpret this, which is it's telling you that's the optimal solution. Second one, reduce cost within decision variable cell. So the reduced cost in decision variable cell, it stands for profit per unit produced. For minus the amount of resources it consumes. So think about it as net addition. Yeah. So profit per unit produced for each of the product minus the amount of resources gone into producing this one product. So for every product, profit minus the resources went into producing that profit. That's what this reduced cost is. Yeah. So for example, a reduced cost of 0 can be interpreted as each unit of aquaspa makes $350 of profit. Yeah, $350 of profit, $350 of profit. Yeah, and that's profits minus what is used to produce that one unit. So we would need 200 units, 200 times 1. We are using one pump. Yeah, we have one pump used, so it's 200 times 1, because every unit of pump we will see it's the shadow price. Shadow price is the price that you would contribute for each unit of pump. So pump in this case would contribute, each additional pump would contribute $200. So we'll get to shadow price later, but imagine this to be the contribution of using this pump. Yeah. So if you had to use this pump, you had to pay $200 because each pump is valued $200. So you built this product that made you $350, but you used one pump, and each pump is at least valued, the resource is valued at $200. That's this value, yeah, shadow price. So you reduce the profit you made minus the resources that you used. So you used one pump, $200 per pump, and we will see what shadow price is, which is how much each unit is contributing. And we are using minus 16.67 times 9, which is for every labor used. We are using 9 units of labor, so 9 times 16.67 minus 0 times 12. Yeah, so we are using these 3 constraints. Each of these constraints have this cost associated with it, or that's what it will contribute in terms of the additional profit. So you're saying, hey, what is my profit minus what is needed to build that profit. So if you do this math, you will get a 0. So that's why it's a reduced cost of 0. This also means that if I had to build, what's a reduced cost of minus 13? It says that if I were to build 1 unit of Typhoon Lagoon, it would reduce my overall profits by minus 13. Yeah, so it's not profitable. My overall profits would go down. So you would reduce that profit by this much if you start to make this to be 1. If you make this 0, then it doesn't contribute anything because it's 0 times minus 13. But if you had contributed 1 unit, then if you had decided as an executive saying, hey, I want to build 1 unit of Typhoon Lagoon, then you would see your profits go down by this much amount, minus 13. Yeah. So that's reduced cost. It also needs some amount of understanding of shadow price. But think about shadow price as how much each of these resources that you have constraints on, how much is each of it valued to overall profits? Yeah, how much does it contribute? So if you had 1 pump extra, you could make $200 more. Yeah, so that's how you can think about that. So that's the resources gone in, and the difference between profits minus the unit cost for each of these resources used will give you the reduced cost. And you can assume this to be how much, if you decide to make this 1 unit of production instead of 0, which is the optimal solution, you would have profits reduced by minus 13. So that's reduced cost. Yeah. Decision variable cells, objective coefficient. So this objective coefficient stands for the coefficient value used in the objective function in these products. For example, we know that each of these contribute, Equispas contribute $350, so it's given to us. So all the unit profit contribution is what the objective coefficient is. It's basically saying this is the coefficient that is applied to my objective function. Remember, it's 350x1 plus 300x2 plus 320x3 is what we're trying to maximize. So these are the coefficients, or the profit contribution per unit for each of these products. So that's objective coefficient. Yeah? And it matches to what's given to us here. Decision variable cells, allowable increase. It will say allowable increase to what? Allowable increase to the objective coefficient. It basically says if 350 were to increase by 100 more, meaning if it were to go from 350 to 450, my optimum solution will still stay the same. That's what it's saying. It's what is the allowable increase on the coefficient of my objective functions for each of these profit, meaning instead of contributing $350 for each Equispa made, if I made 400, if it contributed 450, still I would produce 122 of Equispa. Similarly, if it goes down from 350 to 330, which is it can go down 20 more, I'll still make the same objective decision. Because in real life, you start to see that, hey, profits contribution can change. And so you want to know if some of these contributions go down as to what is the impact on how much items I should produce. So this is very powerful. Like let's say you couldn't make as much profit margin from building Equispas, and you would want to make a decision whether you would want to reduce how much you build. Then it tells you this is the range, 400 to 320, 330 to 400. That's the range in which you would still build the same amount and still get the maximum. So you can still maximize the profit based on the constraints you have for these units. Remember, the profits will change, but it'll still be the maximum that you could with these constraints. And it'll still say that you still build the same amount of same quantities. Yeah. So that's the allowable increase. Similarly, allowable decrease. How much can you reduce the objective coefficient or the profit contribution in this case per unit and still have the same final value of your decision variables, meaning your decision variable still doesn't change. The third part, constraints final value. It's telling you, this tells you how much you end up using. Final value is the same as you had these limits of how many pumps you have, how many laborers you have, but it also tells you how much from it did you end up using. So that I used all of 200. I used all of 1566 of labor, but I didn't end up using all of the tubing. So that matches, the final value here matches to how much you end up using. Yeah. And shadow price in this case tells you how much would your profit increase if you were to get one more unit of, let's say, pump, $200, one more unit of labor, 16, one more unit of tubing, 0, because you've not even used what you have. So if you increase it by one more, you would not make more money. In essence, it's telling you if you were to invest and get more pumps, for each unit of pump you can make $200 more. And shadow price is again connected to reduced cost calculation. Yeah, profits minus units used times the shadow price per unit is reduced cost. So this tells you for every new unit of laborer that you add, you can increase your profits by $16. Yeah. So this tells you the objective function can be even higher if you start to invest in these binding constraints. So you can also quickly from here tell that, hey, these are the binding constraints and this is non-bound constraint, meaning these are used fully, this is not used fully. Yeah, so you can also say that by looking at these limits. So that's the shadow price. Right hand side constraint, this is like what's given to you. Yeah, these are your limits. What are your limits? So constraint right hand side stands for what are your limits. This is what you should be under, and this tells you how much you end up using, final value. And so constraint right hand side is same as what limits you have. An allowable increase to constraint, same setup. Like if you increase and added 7 more pumps, you can expect to make $200 of profits more for every pump. Yeah, so 7 more pumps can increase this profit by $1,400. But it tells you what is the range at which you can use the shadow price. Yeah, so 7 more pumps, you can add 200 for each pump. If you can reduce 26 pumps and you can reduce 200 for each pump in terms of your profit, but your decision variables will still stay the same. So remember, when you make all of these decisions, let's say you do decide to increase for whatever reason, that you decrease the pumps because there was a pump shortage, and you reduce it by 20. This sensitivity report will quickly tell you don't have to change the number of quantities that you build. You will still maximize your profits based on your constraints. Yeah, so that's the reason why you use it, to find out, hey, what is my limits, so that I don't have to change this. And when things change in real life, a lot of constraints change. You don't have to rerun this model, but you can still know that you can use this model with the sensitivity report. But think about it this way. If rerunning the model is not that expensive, you can rerun the model. But a lot of times these models can be very expensive computationally. And so in this case, you want a sensitivity report that gives you all of these constraints. So you don't have to keep running this, don't have to keep asking your engineers to keep running this report, and you can still make decisions based on those constraints. So that's why you have these allowable constraints that give you a very clear idea. How much would my profit increase? But let's say if I told you that you decrease this by 40, then you cannot no longer use this constraint, say, hey, 40 times 200 would be the reduction. 40 times 200 shadow price would be the reduction in my profits. No, it's actually saying this is only okay within this range. And you can only change this one variable at a time. If you see more variables changing, then there's a complex situation where you have to look at the proportion of amount that's changed, and you might have to rerun this optimization again. But all of these changes, all of these allowable increase, decrease, for each of these rows, assume you're changing one variable only. Meaning, if you increase, in this case, let's say 7 pumps, you're not also increasing quantities of aquaspas at the same time. You're just increasing this one item, yeah, and you're keeping some of this, all of these things same. So that's the principle of constancy, which is this only works if you change one variable, and you can still use the static sensitivity report to make decisions. But if more than one variable changes, you have to do a complex calculation to find out the proportional change. But it's best to rerun this if you don't understand that part fully. Just say, hey, I'm going to rerun this report and see if I still get my decision variables to be the same, or it changes, and what's the impact on my output variable. Yeah, it's the same as for allowable decrease. Remember, it reduces optimization function, or in this case profits, for every unit that you reduce by $200 if it's pumps. Similarly, it would reduce $16 for every hour of labor that's reduced for within this limits. Yeah, And for non-binding constraint, you can see that you can go up infinite. That's how you would use this in still, because it's non-binding. So as I said, you can very quickly find out which of these are binding constraints and non-binding constraints. You see slack being 0 gives you a binding constraint. Slack not being 0 shows that there's enough available, so you can increase it. Yeah, and you can also interpret that using the sensitivity report. Alternate solution, this is another example. Let's say you have this other video that I created was on this situation on a car manufacturing. If you see allowable increase or decrease values to be 0, then this points very clearly to there being an alternate solution, where you could say, hey, I will add another constraint to optimize my profits to be equal to $320,000, and then I would reduce and minimize the decision variables. You can add more constraints to get newer values but still the same profits, and you can very quickly find that out from detecting what is the allowable increase and decrease to tell you whether there is an alternate solution or not. All right, so now you're a master of what if analysis. There's so many things you can answer. What if the number of pumps were to increase, and how it would increase my profits? Would it change the amount of different types of products I build? So that's very helpful for you to make decisions. Remember the principle of constancy, which is one variable change is only that's allowed. And if it's multiple, you have to do more calculations to check whether this will still stay the same. And you would know how to use the shadow price, how to use reduced cost, how you would know what are binding constraints, non-binding constraints, how would every unit increase or decrease change the optimal value, when would it change, when would it not change, what bounds would trigger it, and how you could still keep the same amount of decision variables as same, which is the same value, but still the optimum objective function could change. Yeah? So that is the sensitivity report on how you go over it, and hope that's helpful. Thanks.